Hi, this is Augusto Salomão Bon Schlegel. I'm professor at Federal University of Grande Dourados, and I'm presenting this work entitled Flow Dynamics and Aerodynamic Forces on an Adapted Ahmad body at Moderate Reynolds Numbers through Numerical Simulation. When we talk about vehicle aerodynamics, we are concerned mainly about two things. The first is fuel consumption. We always try to minimize fuel consumption and improve the vehicle aerodynamics. And the second concern is related to the stability and safety of this vehicle. The most studied vehicle to evaluate aerodynamic forces is a model proposed by Ahmed in 1984, the so-called Ahmad body, which is basically a simplified vehicle model which has a broad nose at its front part and a slanted angle, a chamfer, at the rear of the vehicle. So this configuration creates some structures after the rear part of the vehicle, and this causes impacts in the aerodynamic forces. As an example here, we have the flow visualization in wind tunnel, when we see the flow behavior past the Ahmad body, and some examples which shows the development and the structures behind this body. In the present work, what our study concerns the influence of this the addition of a fillet between the top surface and the slanted angle. So we added this change to the benchmark, to the original geometrical configuration, to evaluate the influence of this curvature at the rear part of the vehicle. So we tested 6 different curvatures from 0.5 millimeters to 50 millimeters, and also the benchmark, the original geometry. These tests were run for different Reynolds numbers from 4,800 to 48,000, and for this range of Reynolds numbers we evaluate the flow dynamics as well its impact on aerodynamic forces, mainly drag forces. So to attain this objective, we use a numerical model using OpenFOAM software version 7.0. At those Reynolds number range, we evaluate 4 different velocities for 7 different geometries, which resulted in 28 different cases. We decided to use a 2D model by extruding the front patch of the 3D mesh. So we had the 2D model with 0.3 million cells, which was pretty much lighter. Our model is a transient model, and we use the transient solver, which is the piezo form. The initial condition was actually calculated using a steady state solver, which is the simple form. So we used the result from the steady state problem as the initial condition for the transient problem. To integrate in time, we used a second order backward scheme and a variable time step, so that this variable time step always should generate a Coulomb number equal or less than 1. For the turbulence modeling, we use a K-omega SST with 3% of turbulent intensity, and for the advective terms in the Navier-Stokes equations, we use the second order upwind. 1 characteristic of this model is that we had represented the relative motion between the armed body and the ground by imposing at the ground the inlet velocity. We have zero velocity at the armed body, no slip condition, and at the lower bouldering condition at the floor we had the inlet velocity. So this had created the relative motion. So for this range of Reynolds numbers we have found some data in the literature, and our results stay somehow between this data with drag coefficient about 0.35. So considering the limitations of a 2D model and some premises we have considered, we concluded that this model is representative. So for the first velocity, 5 meters per second, which represents Reynolds number of 4800, what we have here is that for the benchmark solution and the first radius we had about the same value of the drag coefficient, and as we increased the radius we had an increase in the drag coefficient. This can be justified by the larger recirculation zone behind the vehicle, as we can observe here in radius 10, 15 and so on, and this broader recirculation region promoted a larger drag coefficient. As we increase the Reynolds number, we had observed at the first radius here and periodic behavior, which is present here by these structures that interact with the ground, which is also moving, and this periodic behavior is presented in the smaller radius. As we increase this curvature, which is the radius 35 and 50, we have a lower drag coefficient and stable behavior. For the next velocity, 20 meters per second, which leads 19,000 Reynolds number, we still had some periodicity in the lower curvature geometries, and this periodic behavior has been extinguished as we increase the curvature. If we continue increasing the Reynolds number, what we observe is that this periodic behavior has a lower frequency, and the rear part of the vehicle, the flow, we had a smaller recirculation area. So here we can observe a lower drag coefficient. So for this study we have observed, using our simplified numerical model, that we have lower drag coefficients for higher curvatures at higher velocities, and we have lower drag coefficients for the low curvatures at low velocities. The rear curvature brings some benefits in terms of drag reduction only for Reynolds above 9,000. We also have observed some dynamic behavior, and that is shedding, the periodic behavior for low curvatures and for Reynolds number between 9,000 and 19,000. So this is it. Thank you for your attention.